We are now in part 4 of this discussion on the Kelvin, Helmholtz and the Rayleigh-Taylor instability. Let me first recap what we have done in the previous lectures. We are looking at stability of two superposed streams of fluid with different densities ρ1 and ρ2 and different velocities u1 and u2. These two streams meet at the interface z equal to 0, and at the interface we also have surface tension. Because the problem is done with the inviscid incompressible approximation, we can basically use the velocity potential to describe the velocity field. And the main governing equation that we have is equation number 4, which is the Laplace equation for the velocity potential in each of the streams. Each of the fluids satisfy the Laplacian of phi, where phi is the velocity potential. The gradient of phi is the velocity as far as the base flow is concerned. We first derived the full nonlinear equations. That's basically equation number from equations 2 to 8. They are the full nonlinear equation for the stability problem. Then we basically perturbed the system, introduced a disturbance of the form shown in equation number 9. And we say that the perturbations are very small in magnitude, and therefore we can linearize the equations about the base state. The linearized equations about the base state are seen on your screen, going from equation number 10 all the way up to equation number 13. So the boundary condition terms are basically 11, 12 and 13. They are the boundary terms in the far field. Then we have two sets of boundary conditions at the interface. One is the kinematic condition, that's equation number 12. And then we have the normal stress balance at equation number 13. If we do not have surface tension, then the pressure is continuous. But because there is surface tension, the pressure at the interface undergoes a discontinuity, and the curvature itself in the linearized form is shown in equation number 13. Then we assume the normal mode form for the solution, which allowed us to convert the linearized partial differential equations into a set of ordinary differential equations. These ordinary differential equations can be further combined, primarily the Laplacian. If you see, we can get the solution of this Laplacian. The Laplace equation for phi1 simply gives me an exponentially decaying solution. The exponentially decaying solutions in both the streams are shown also on your screen, that's 16 and 17. Then we can take advantage of the kinematic conditions and relate the coefficients or the amplitude of these eigenfunctions 16 and 17, that's a1 and a2. We can write a1 and a2 in terms of the amplitude of the displacement of the interface, that's eta hat, that's 18. So a1 is now expressed in terms of eta hat, a2 is also in terms of eta hat, and s, as you know, is the complex growth rate, u is the velocity in both the fluids, and then m is basically the wave number in a three-dimensional setting. So m would be square root of k square plus l square, where k is the wave number in the x direction, the streamwise direction, and l is the wave number in the span-wise direction, that is into the screen or out of the screen. So finally we were able to obtain a dispersion relation by taking advantage of the last equation, that is the normal stress balance, and we get a dispersion relation. Note that eta hat, the perturbation amplitude of the interface, does not matter. In fact, for a linear problem, the amplitudes will drop out as expected, and therefore the dispersion relation that you can see on your screen is a simple quadratic equation, that's equation number 19. Now we can combine this in the form that's shown on your screen. I can write it in terms of a simple quadratic, s square plus as plus b, where a and b involve all the parameters of the problem, the wave numbers, the velocities, the densities, and so on. This is the most general dispersion relation for the superposition of when two superposed streams, they meet at an interface with surface tension present. We can obtain the general solution of this problem, and the general solution is also shown in your screen. That's equation 19 is the general solution, but it's sometimes more useful to look at special cases. The first special case that we looked at was the Rayleigh, not the plateau instability. Please correct this. This should be Rayleigh-Taylor. This should be the Rayleigh-Taylor case, right? And what we found in the Rayleigh-Taylor instability is that the flow is unstable when the wavelength exceeds a certain critical value, and that certain critical value turned out to be 2 pi times the capillary length. Now recall that capillary length is the length scale where surface tension and gravity are in balance. So if you are at a length scale much smaller than the capillary length, then surface tension dominates. If you are at a length scale which is much larger than the capillary length, then you should expect gravity to dominate. So this is the problem that we've looked at, the Rayleigh-Taylor instability. Now we are looking at the Rayleigh, we want to look at the effect of velocity field. Now the effect of velocity field, by the way, here's a small exercise for some of you. You can also look at it in terms of an energy cost. Here I've tried to physically explain the Rayleigh-Taylor instability in terms of these undulations that are created, and these undulations lead to, interface undulations lead to perturbations in the local density field. You can think of them as a density perturbation that is created at the interface, and depending on the nature of the density perturbation, whether it's positive or negative, it will decide whether the flow is going to be unstable or stable. Of course, only for if you exceed the condition, if you satisfy the condition that lambda is greater than 2 pi LC. But we can also look at it from energy perspective. We can write down if there is a small perturbation, we can find out what is the change in the gravitational potential energy. We can also write down the change in the surface energy for a given wavelength and ask, will the perturbation favor reducing the energy or increasing the energy? Now, if you're in an unstable configuration, that is, if a heavier upper fluid is heavier than the lower fluid, then it is favorable for the perturbation to grow because it decreases the overall potential energy of the system. So, but in the other case where rho2 is less than rho1, meaning the upper fluid is lighter, perturbations actually increase the energy of the system, and therefore a flat interface is more favorable. Now let's look at the part 4, the final part, which is the case where you have different velocities. I have again written this down I've written down the general dispersion relation that we have already seen for your benefit. This is the equation that we have, the quadratic equation. We'll now be looking at the Kelvin helmholtz instability. So we'll do it in a very special limit. We'll set let densities be the same. So which means that no effect of gravity. If you can see in the term B, we have this term mg times rho2 minus rho1 divided by rho1 plus rho2. That term is going to go to 0. And therefore, I will simply have, let's write down A. We don't need to do this, but by doing this, we can basically focus on the effect of velocities primarily. The first thing that happens is, if I write down the expression for A, I simply have IK times U1 plus U2. That's the expression for A, because here rho1 and rho2 becomes rho0. So rho0 comes out of the thing in the bracket in the first term. The denominator becomes 2 rho0 and the 2 cancels out and the rho0 also cancels out. What about B? B essentially becomes minus k square over 2 U1 square plus u2 square. The gravity term drops out, plus m cube gamma by 2 rho naught. This is basically my coefficients of the quadratic equation in the dispersion relation. And so S essentially becomes minus A plus or minus A square minus 4B by 2. So it means instability only occurs if A square minus 4B is greater than 0. Let's look at this case. A square minus 4B essentially becomes minus k square of u1 plus u2 whole square minus 4 times b, that is minus k square over 2 u1 square plus u2 square plus m cube gamma by 2 rho naught. Right? This is a square minus 4b, and let's simplify this further. I have k square, that will take it to be common. I have u1 square plus u2 square plus 2u1 u2. Then the next term would be plus 2k square of u1 square plus u2 square minus 2m cube gamma by rho naught. Now remember, this quantity a square minus 4b, this quantity has to be greater than 0 for an instability, right? And therefore I have k square of u1 square plus u2 square minus 2u1 u2 minus 2m cube gamma by rho naught has to be greater than 0, and I simply get k square times u1 minus u2 whole square minus 2k cube gamma by rho naught. This has to be greater than 0. So u1 minus u2 whole square should be minus, sorry, not k cube, this is m cube, minus 2m cube gamma by k square rho naught greater than 0. Or I can simply write u1 minus u2, the magnitude of this quantity has to be greater than 2m cube gamma by k square rho naught. Right? This is what we have. For a 2D flow, m square, which is square root of k square plus l square, essentially becomes square root of m becomes this, which is k. In other words, if we consider a 2D case, just for the sake of it, without any loss of generality, I simply get we get u1 minus u2 magnitude will essentially be 2k gamma by rho naught. Instability for a 2D perturbation. It's not a 2D flow, sorry, this is a 2D perturbation. By 2D perturbation, I simply mean for this case, the normal mode will be eta hat times e power I kx plus st. We are ignoring the variation in y. Now you can actually show that the 2D perturbation, it's sufficient to look at the 2D perturbation because there is a way to prove that the 2D perturbation is more unstable than the 3-dimensional perturbation. So for any 3-dimensional perturbation, there is a 2-dimensional perturbation which will grow faster. Okay, there is a proof for it, but I'm not going to go into that proof because it's convenient to just look at, let's focus on the physics of the problem. So we have u1 minus u2 is this. So let's basically look at what this relation tells us. It tells us that if you have surface tension, then once the velocity difference between the upper and the lower streams exceeds a certain critical value, you have an instability, right? So and also notice that the quantity in the numerator has a k that is present, right? It has a k that is present. So instability will only occur when you uh, if the k becomes very, very large, the quantity on the right hand side will become very large, and no more, and it's no more, this inequality will not be satisfied anymore. So now that we have this u1 minus u2, this cutoff, we have this expressions for a and b, right? And therefore I can also write down the full solution for s, and I leave it to you to work out the exact expression for s. S would just be minus a plus or minus a square minus 4b by 2s by 2. But essentially, if we make a plot of the real part of s versus k, what we now have is, if k is small, small k would mean long waves, and large k would mean short waves. So let me just illustrate that to you. Long waves means these are long like this, whereas short waves have a much smaller wavelength. That's what we mean by short and long. Note that there is no length scale in the problem that is present. So short and long should be interpreted in terms of a cutoff wavelength. What is the cutoff wavelength? We can actually write down if k becomes greater than some cutoff wave number, which is essentially given by u1 minus u2 whole square into rho naught by 2 gamma, then flow is stable, or rather there is no instability, right? If you look at this inequality, I can extract k in from this inequality, and it says that if you exceed k beyond that, then you will have no instability. So if you want an instability, k has to be less than k cutoff. So essentially, let's say the k cutoff is somewhere over here. That's k cutoff. And once we know the k cutoff, I can simply calculate lambda cutoff will simply be 2 pi by k. That is 4 pi gamma by u1 minus u2 whole square of rho naught. That's the lambda cutoff, right? So what does this actually tell us? It tells us that once you exceed a critical cutoff, there is no instability, and this therefore tells me that short waves are stabilized. And on the other hand, long waves are unstable. Let's look at it physically, what it means. If you are basically having a wave which is very, very long in wavelength, so you are operating at very large length scales, and therefore surface tension effects would not be very important. And I think it may be worthwhile writing down the full general solution. The general solution for S would be minus B, that is that's what we have, minus A plus or minus minus A, that's minus IK u1 plus u2 plus or minus a square minus 4b, and we calculated a square minus 4b as simply this quantity here, which is k square of u1 minus u2 whole square minus 2m cube gamma by rho naught whole divided by 2, right? Now notice that well, let's do it for 2D case. So in the 2D case we have k cube. We simply have 2k cube. M becomes k in the 2D for a 2D perturbation. This, let me write down, this is 2D perturbation. Now notice that in the absence of surface tension, I will simply have in the long waves, when long waves meaning when k becomes very, very small, if you look at the term under the square root, you have k cube versus k square. So for small surface tension or for no surface tension, I simply have minus ik u1 plus u2 by 2 plus or minus k times magnitude of u1 minus u2 by 2. So this quantity is nothing but Si, that's the imaginary part, plus or minus Sr. So I definitely have an unstable mode, and the unstable mode essentially grows linearly with a k. As you increase k, you have an instability. So in other words, I can just write down, for large k, surface tension would not be important. I can simply say, in the absence of surface tension, there is an instability whose growth rate increases linearly with k. Correct? But, and that's the linear growth for this case. This is a gamma equal to 0 case. So it tells you that in the absence of surface tension, waves of all wavelengths are unstable. Okay, the shorter the wavelength, the more unstable the wave is. The longer waves are stabilized, but shorter the wavelength, the more unstable the wave is. Okay, but the moment you introduce surface tension, we have introduced a cutoff which says that for an instability you have to be below this cutoff, and that is not surprising because if you look at the quantity under the square root and the term that I'm highlighting, this comes with a negative sign, and that's a k cube term. So when k becomes large, k cube term will start dominating over the k square term. Surface tension will start dominating, and then there is a truncation that happens, and you will initially grow as if there was no surface tension because you are still in the long wave limit, and then you have a cutoff that happens. You have some kind of a cutoff that happens. So this is the dispersion relation. Dispersion relation for KH instability with surface tension gamma. So surface tension basically provides a cutoff where it basically stabilizes very, very long, a large K limit, or short waves are stabilized by surface tension. That's not surprising because if you see the little sketch that I have made here, that I'm highlighting for your benefit, if you compare it to the long wave, the case where we have long waves, the moment you create tiny undulations, you are essentially increasing the surface area, and therefore surface tension effects become more important, right? So now we will look at a few other special limits. We can also make a plot, by the way, of SI as well. Maybe I should mention that as well. SI is not equal to 0 and implying that the unstable mode is also traveling. The wave, it's actually traveling, and therefore it's also and while it's traveling, it's also growing. Now you can also write down the phase velocity of this motion. The phase velocity or the phase speed will simply be, let's call the phase speed as c, that will be si by k, and the sign is not very important. The phase speed is u1 plus u2 by 2, which means that if I just ignore the sign, the direct sign will tell us the direction. It tells me that the phase speed, the magnitude of the phase speed, is just the average of the two fluids, which means that if you have two fluids with different velocities u1 and u2, there is an undulation on the surface, and this undulation would travel and amplify as it's growing, as it's moving in the flow, provided the wavelength is such that it is below the cutoff wavelength. Now, if you have two streams which are in the opposite direction and equal in magnitude, for example, if I can always consider a situation where I have one stream this way with a velocity of u1, u2 is equal to, let's say, plus v. I could have another stream of the same magnitude u1 is minus v, then I can immediately say the phase speed c will be 0, because u1 and u2 will cancel each other out. But note that the other quantity, which is the growth rate quantity, will not. Right? It is u1 minus u2. In fact, in this case, it becomes 2v. So if this happens, then S essentially becomes just plus or minus k times v. Well, let's write down the full thing here. So I have half square root of 4k square v minus 2k cube gamma by rho naught. This is the growth rate. Growth rate SR will simply be half square root of 4k square capital V minus 2k cube gamma by rho naught. So this is my growth rate. I'd like all of you to double check these calculations. So we have a wave which does not travel when the two streams are in opposite direction, because then there is no net preference for left or right. That's another way to look at it. There is no up and down in this problem because there is no gravity, so there is no meaning for upper fluid and the lower fluid. But if there was gravity, gravity would provide us some kind of a reference in which using which we can say this is up and this is down. But since we don't have that, we only can still say left and right. That's because we have velocities, two different velocities, but now if the two velocities are in opposite direction, then again there is no special preference for left and right. And what's likely to happen is that the nature will provide a solution where the wave will just not move anywhere, but it will just amplify. So this is a standing wave that you get, right? So let's basically look at one more case. This is ocean surface. This is an idealized ocean, let's put it this way. The idea is the following. We have a surface of the body like this. The density rho 1, let's say, is water, that is 1000 kilogram per meter cube. The density rho 2 is rho air, which is around 1 kilogram per meter cube. But let's say we have a calm ocean. Velocity at the bottom is basically 0, and the velocity at the top, we'll say it's capital U. So this is calm ocean with wind on top. So we have a wind that is blowing on the top, and we have a calm ocean. So let's write down the dispersion relation for this case. So we just have to substitute U1 is equal to 0, and let's see what simplification we get. Our original equation was S square plus AS plus B equal to 0. Now A simply becomes 2ik. I'll do it in the 2D limit. Rho 2 U2 divided by rho 1 plus rho 2, and this is can be written in the variables that we've written. Rho 2 becomes rho air, U2 becomes capital U, and this becomes rho W plus rho air, which is approximately 2ik rho air of U divided by rho W, because the denominator rho W plus rho U is approximately just the density of the water. Air density does not contribute much to this case. What about B? Now it is minus k square. I would like you to try and simplify from this here. Several terms can be dropped out. For example, this will drop out from this analysis. We can also say that rho 2 minus rho 1 that we have essentially becomes, rho 2 becomes rho air minus rho W, where rho air plus rho W. This is approximately minus rho W by rho W, and approximately it's minus 1. That's what we have. So I'll do this in the 2D limit again. So in the 2D limit, we simply have, in the 2D, for the 2D perturbation, we simply have minus k square rho A U square by rho W plus GK. We will also consider a situation where, let's say, surface tension. What's the value of the surface tension that we have here? I have plus m cube gamma, or k cube gamma, plus k cube gamma by rho W. This is basically the final expression that we have here. Now you can basically ask, what is the velocity that I need to have? So if I have a wind that is blowing, with a velocity of u at the top, what is the minimum speed of the wind such that I get an instability? Correct? That's the kind of question that we are interested in. So instability occurs if a square minus 4b is greater than 0, right? I would like you to try and write down this expression on your own and see if you can work out the exact, simplify this expression and get a dispersion relation. Now note that there are only the three parameters that we have here: density of the air, density of the water, and the velocity of the free stream. That's the only three parameters. And the question that we are asking is, if we have two different, if we have a free stream that is moving at the top, then we can come up with an expression for the velocity. Or let's put it this way: if I put a square minus 4b is greater than 0, this essentially would mean that u has to be greater than a u critical. Okay, And what is the expression of that critical? This critical value will be something like G by K plus sigma times sigma times K, or gamma times K. So I would like you to work it out yourself, this expression. And the idea is the following. The idea is the following, that if we want to find out this velocity of the wind versus K. So if your velocities, if your wave numbers are very, very small, which means that if you have long waves, then in such cases gravity would dominate, and if you are very short waves, then surface tension would dominate. So if you look at this expression that we have here, U critical or U versus K, then the curve essentially would look like this. At very, very small K, this value is very large, but then it basically hits a minimum, and then again it increases linearly, right? So what we want to find out is what is the value of this minimum. So this minimum is obtained by taking the derivative of this UC with respect to K and setting that quantity to 0 and getting the U critical for that particular K. Okay. So I will leave it to you to work out this analysis. I will be providing this as an assignment as part of the course. All that we have to do is calculate the expression for UC, take the derivative of UC with respect to K. Basically that will correspond to the minima in this curve. So I'll give you some numbers here. So for example, we should expect if we take water with density of water to be 1000 and surface tension of water air interface is 0.072 Newton per meter, gravity to be 10 meters per second square, then we can work out the value of the K. Let's call it as K min. The value of the K min will approximately, this is my calculation, it's coming out to be about 10 power 3 by root 7, and U min that I am getting is around 7.27 meters per second. It says that if I have a wind on a calm ocean with surface tension that is present, if I exceed the velocity of 7.27 meters per second, approximately 7 to 8 meters per second for such a system, then I will generate an instability on the surface and I will start seeing waves on the surface, right? These would be capillary waves. Now, if you are basically looking at wavelengths much larger than this K min, you have capillary waves. On the other side, you have gravity waves. So here, this is where gravity dominates. So for very small wavelengths, if you want to generate waves of very large wavelength or very small K, then it means that you have to push the wind at a much higher speed because gravity would prevent it from creating large undulations on the surface. So gravity is a dominant regime there. And on this side, you have a surface tension dominant regime. So let's say if you want to create ripples of very small scale, then again it means you have to push it fairly fast because this curve says that the velocity where you start seeing an instability is again keeps increasing linearly with K. So if you are above this curve, if you're above this curve, you're in an unstable region, meaning if you have a velocity that is falling for a given wave number, if the velocity is falls in this region, then you can be assured of an instability. But if you are outside that region, you are stable. I'll call it stable, but to be honest, it is neutrally stable, meaning you can have oscillatory states, but you cannot, if you create an undulation, the undulations will persist forever because it's an inviscid system. But otherwise, if you want an instability, you have to exceed a particular critical velocity. Now, what we have, I think this sort of brings us to the conclusion of the discussion on shear flows and surface tension. Note that surface tension can play a fascinating roles in many systems, instability problems. Next time you see a calm body of water, or take a glass of water in a container, or take some water in a container and try to blow air above it, and notice what happens to that air. If you basically blow it very hard, and of course you have to blow it parallel to the surface, then only then will you get an instability. But if you blow it very gently, you are likely to generate tiny capillary ripples, which will basically just decay down. Okay. This is a very simple theory, which, because we've ignored effects of viscosity, in most cases in a problem like this, viscosity is not the primary, does not play a very important role as far as the instability is concerned. Viscosity plays an important role in stability, which means that any disturbances that are there, if they are neutrally stable, if you have oscillatory states, then viscosity can ensure that you have a decaying solution. So these are open flows as in there are no walls. In such cases, viscosity has a limited role. In most cases, viscosity has a limited role as far as instability is concerned. Of course, it is true that if you have viscosity, the growth rate that you see is expected to be slightly lower than the equivalent inviscid case, because there is some amount of damping that viscosity produces, and that results in a slightly lower growth rate. So with this, we conclude the discussion on the Kelvin, Helmholtz and the Rayleigh-Taylor instability. I'll see you around in the next class. Thank you.